Well, good morning, everyone. Thank you for inviting me to come here. I'm certainly a newcomer. This is the first time attending this AeroSpace Blitz. I will tell you some story about the new initiative we have taken on as CU campus called Quantum Initiative. And in fact, we named the initiative name called CUbit. BIT, as you know, it's a quantum information processing, the basic unit. And we thought this is a cute name, CUbit. And this little symbol, if you don't recognize it, it's called a cat in quantum mechanics, meaning a state that's in a pure quantum mechanical state. And I'll tell you a little bit about the reason why we are doing that. You probably have heard there's a huge buzz going on nationally. It's called a Quantum Initiative, National Quantum Initiative. Congress has passed the authorization bill for the next 5 years. There will be $1 billion invested in the quantum. In fact, in this year's presidential request for appropriation, he had already put in over $1 billion for AI plus quantum, and it was quantum being a few $100 million for this year, for the coming fiscal year alone. And we figured if the nation's investing billions of dollars in the coming decade, and the Boulder being a capital of quantum mechanics in the nation, we must be getting some hundreds of millions to do research work. And that's part of the reason, not really because we are after all these dollars, but because we really find it's a great opportunity to pursue fundamental research. You know, when we were building this qubit, the idea is that science first. As we heard today from Jay, this is a place where fundamental scientific research is at the very forefront, both internationally and nationally. And we have identified 4 important pillars for quantum technology and science, whether it's quantum sensing, or quantum computation, or quantum communication, quantum links, and quantum materials. And we have very strong research going on campus here. Based on these fundamental research, standing on these 4 pillars, we hope that we'll be creating innovative education programs for both graduate, undergraduate, training, because industry is calling us saying there's this big wind shift towards quantum technology. We do not have, I actually literally received calls from Boeing saying we have 200 engineers who can do anything engineering, but they haven't heard about quantum yet. Can they come to our campus and have a training? So we want to be sensitive to the industrial needs to be able to develop not only based on scientific work, but doing the first, the most innovative job on the science, basic research, but start to develop technologies that can translate some of the most advanced scientific understandings and the technologies into something into the commercial world, and that will help the U.S. industry and the workforce training and the build economy and so on. So as you can see, this is the necessary multidisciplinary research area, and it's being formed by JILA. That's where I'm coming from. It's actually a joint research institute between NIST, National Institute of Standards Technology, and the CU. Physics, engineering, there are a lot of activities going on in engineering. You're going to hear from Svanya later after my talk, from chemistry, biology, and so on, and including NIST already as one of the partners for this new quantum center on CU campus. We'll be pursuing some grand challenging goals, and I will give you one specific example towards the end of my talk. But these are based on existing strength we already have. There's a world-leading strength in quantum physics, and really try to solve high-impact, outstanding problems in quantum. Can we build a quantum computer? Can we really put optical atomic clocks at the level of 10 to the minus 21? And we heard about lasers propagating in the atmosphere. Can we send time back and forth, building Earth network that through the atmosphere down to the Earth and give the time at the level that we can see gravitational waves, not gravity waves this time, it's actually real gravitational waves. And then try to translate that forefront of science into technology, into something that people will be useful for in daily life. So this will, we also hope that will have a huge impact on, as I mentioned earlier, to quantum information and science and technology sort of workforce training, education, and have industry engagement, such as you. And then maybe just give you a couple slides. I figured that slide was a little heavy. And I want to just, as a scientist, I always find interesting to tell you, a little bit about science. What is quantum? If some of you haven't thought about quantum for a little while, maybe after your college, quantum is a basic science governing microscopic world, right? You have seen something that's really counterintuitive. When I tell you a person can be in place at the same time, can be in two different places, you will say, get out of here. How can that be true? But when we talk about atoms, electrons, when I actually play with, I build atomic clocks. And that's the life we deal with every day. The atoms is in two different places at the same time. It sounds very weird. In fact, you cannot think of atom as a particle. It's a wave until you make a measurement. So this is just like a look at the skier. Somehow his wave function was able to permeate through this tree. Sounds very strange, but in quantum mechanics, that's what we do. And for example, an atom can be in ground state, spin down, spin up, but it can be simultaneously in both spin down and spin up. You may have heard Schrödinger's cat. The cat can be live and dead simultaneously. How can that be true? It's called a coherent superposition. And this is probably one of the most mysterious aspects of quantum mechanics. And in fact, the new technology, however, does depend on this. In fact, you have heard of quantum mechanics, right? Everybody uses lasers. I have a laser in my hand right now. We use computers every day. This is being projected by a computer. For health science, and MRI is just a daily routine medical procedure. All of these technologies developed in the 1960s, 50s, and so on, I would actually based on I would call the first quantum revolution, where you understand and control a very large ensembles of electrons and photons. You can have, because of that, you can actually build lasers, build medical science devices, build navigation systems like a GPS, semiconductor industry electronics, and so on. They can all be developed through this first quantum revolution. And remember, those first quantum revolutions are treating electrons and the photons as individual particles, large ensembles of those. You are basically harnessing a herd of those electrons, like photons. For example, this laser, the reason why you can see such a bright spot is because there are many, many green photons coming out. They do not interact with each other, but nevertheless, you train them to be behaving the same way. That's what a laser is. The new revolution, which we call Quantum 2, is now emphasizing on building things from ground up. We are going to learn how to control individual electrons, atoms, and photons with a superposition. There's a weird quantum mechanical properties where things can appear simultaneously in two locations, or frequency can exist simultaneously in multiple spectrum. And by controlling them individually, then we can bring them together, have them interact, basically at will, controlling the quantum system at will. That brings in the so-called quantum entanglement. That lies in this basically unlocking this new powerful capabilities for computing, for sensing, for communication. And I just give you a quick technology and scientific frontiers. For example, in Paris, people now can measure individual photons as they fly through a cavity. You can not only measure the presence of a single photon. By doing this measurement, you won't destroy that photon. It's really amazing. Like, you will say, how could you do that? But this is the modern technology. In fact, we have that capability in our lab down there in Jella. Oh, excuse me. We cannot control individual atoms. This is the experiment I'm highlighting from both from Harvard and from MPQ, Max Planck Institute of Quantum Optics in Germany. And the same capability exists here in Jella. We can use this kind of capability to build the new generation of atomic clocks that is now reaching at the level of 10 to minus 18, which means it's actually sensitive to gravitational redshift, Einstein's general relativity, with just a 1 centimeter change on elevation on the surface of the Earth. So this kind of a clock will go out of the lab, become the incredible sensors of measuring absolute potential. You can know if polar ice cap is melting a little bit, sea level goes up a little bit. Clock will tell you that in a very sensitive fashion. And we can build now new devices, nanomechanical devices, to be able to transmit quantum information and connect them up. And of course, the last but not the least, the potential capability of building a quantum computer that will revolutionize the computing industry. So these are very exciting new platforms, and it's based on something which is very tangible. You just have to do a really, really good job of bringing these multiple atoms, photons, electrons together in fully controlled quantum manner, bring them together to interact with each other and guide them. So I'm going to give you, before I end, I want to give you one particular example, and I call it grand challenge example. The goal is to be able to take the best atomic clock that we can build, or magnetic sensors, or really advance the forefront of so-called quantum sensing, time, space, field, potential, and then translate that very much fundamental understandings of fundamental quantum science, and really unlock the mystery of the universe per se, and then translate that into a robust network of quantum sensors. So at CUbit, we want to emphasize the so-called vertical integration, where you can see this maybe the science heavy on this side. For example, we have clocks now measuring at the level of 10 to minus 18, I was mentioning earlier. And we see the potential to improve the clocks to 10 to minus 20, 10 to minus 21 in the coming decade. If a clock becomes so good, what can we do? You will be able to move the clock, as I mentioned earlier. You can do relativistic geodesy. You should be able to control the navigation in deep space. You will be able to measure the quantum mechanics, and Einstein's general relativity start to come together. Because within a coherent superposition of, when I said atom can be here and there simultaneously, what if they were here and they lower their position down a little bit there? The time is different. Because Einstein told us, because of the Earth, the space-time is curved. And if you move them by just a few microns, the time is actually different. This is something mind-boggling, right? When GPS was created, people actually at the time was still not fully convinced Einstein relativity was correct. When the satellite was launched in the 70s, some people said, well, maybe we shouldn't put in the general relativity correction of the time. And look what happened. If you put in the correction, cars can navigate accurately. If you don't, the cars will be driving around aimlessly. So we are talking about 5 orders of magnitude enhancement of the current GPS technology. Okay, so so we want to probe some of the very deep questions of whether the universe has dark matter, because we can build clocks to sense that. We want to measure whether the space-time curvature has influence in quantum mechanics. That's something we can actually sense in the coming decades. But meanwhile, it's very exciting. This frequency comb was mentioned. The comb is going to be able to translate all the optical frequencies to anywhere, microwave frequencies to build a clock. We can use that to build a network. In fact, there is an optical link between the Jella building and the NIST building. We're actually transmitting times in space with Nate Newberry and so on. That's where Greg came from. And eventually, I envisioned the clocks will be in space like that. And so you can see there's a lot of opportunities between science, technology, and applications. We have eventually we would like to have clocks to be compact like this. And so there's a lot of components like a fast atomic clock, frequency comb technology, packing technologies, quantum networks, and so on with industrial involvement. And in order to really fulfill this grand challenge, it requires us to put together the strength of NIST and CU and building opportunities of a collaboration between engineering and science, and really pursuing fundamental science and the technology together. And I think the opportunity is abundant, and I think the research forefront is very exciting, and I also think there are a lot of opportunities for industry to be involved. So with that, I think my time is up. I just want to put the slide up as a summary for the CUbit. And I hope you see this is a very exciting new opportunity that our campus is launching. We would really want to build Boulder as the national hub. I would even call it the international hub or capital, as our Vice Chancellor Terry Fees always say, as a quantum capital of the world. Thank you very much.